We toss around terms like the cloud and wireless so casually, it's easy to assume our digital communication is completely untethered. But that floating abstraction is largely an illusion. Underneath every app and high-resolution stream is a tangible physical highway. In engineering terms, we call this network media, the literal channel required for any message to travel from a source to a destination. Even if you are holding a smartphone with 0 cables attached, that wireless connection has to hit a physical wire almost immediately, usually at the nearest router or cell tower, to get anywhere meaningful. Modern networks rely on 3 primary mediums to bridge those gaps: metal wires, fiber optics, and wireless transmission. Our invisible digital world is actually chained together by millions of miles of physical infrastructure, encoding your data into raw electricity, pulses of light, and electromagnetic waves. Deciding exactly which of those mediums to use is an incredibly precise engineering and economic puzzle. Before a single cable is laid, a network architect has to balance 4 strict constraints. First is distance. Physical signals inherently degrade as they travel through space, so the media must be measured against its maximum viable length. Second is the environment. An architect must evaluate if the cable is going to sit in a pristine, climate-controlled server room, or if it will be exposed to extreme outdoor weather and interference. Third is bandwidth. The specific speed and volume of the required data directly dictate the physical limitations of the cable. And fourth is cost. You have to weigh both the capital required to purchase the media itself and the manual labor required to actually install it. Every successful network on the planet exists because someone perfectly balanced distance, environment, bandwidth, and cost. For local networks, the clear winner is twisted pair cabling. It is the most ubiquitous network media and the bedrock of the modern Ethernet standard. Stripping the jacket reveals internal wires grouped into 4 twisted pairs. This spiraling architecture physically reduces electrical interference, canceling noise from the outside and adjacent wires. Notice the color coding: 1 solid wire and its partner the same color striped over white. This pattern guarantees technicians can perfectly identify and align the exact same wire at both ends of a massive cable run. But it does have a vulnerability. Because twisted pair relies on pushing raw electrical impulses, the signal can only travel so far before it degrades completely. It is an engineered compromise, trading extreme distance for cheap, highly reliable localized connectivity. Long before twisted pair dominated the office, there was coaxial, an older, heavy-duty predecessor engineered for tasks that standard copper wires simply couldn't survive. Coaxial is built like a tank. Right in the middle is a single, rigid copper core, conducting the actual signal. Surrounding it is a thick layer of insulation, followed by heavy braided metal shielding, all wrapped up in a tough outer jacket. That massive metal shielding fiercely protects the inner copper core from harsh outside environmental interference. Its massive protection creates a highly reliable transmission line. This is why it historically served cable TV companies, pushing broadband video directly to your home. Those same high-frequency capabilities also make it essential for connecting the highly sensitive components found in massive satellite communication systems. Coaxial trades flexibility and low weight for sheer durability, providing a heavily shielded conduit specifically for critical broadband signals. Eventually, copper wires hit their absolute physical limits. Electrical signals, no matter how well shielded, degrade over vast distances. To solve this, engineers shifted the underlying physics. Enter fiber optic cable, completely abandoning electricity to encode data into pure pulses of light. The core of a fiber optic cable consists of individual glass strands, roughly the diameter of a single human hair. Acting as perfect internal mirrors, they bounce light pulses down the cable for miles without losing the signal. And because they use light instead of electricity, they are completely immune to any external electrical interference. These microscopic fibers carry massive amounts of digital data at vastly higher speeds over incredibly longer distances than copper ever could. This capacity scales beyond desktops. It powers global internet backbones, massive data centers, and provides the precise accuracy required for advanced medical imaging. Fiber optics represents the ultimate scaling of network media, harnessing the physical speed of light to carry the heavy digital weight of the modern world. To build a functioning system, a network architect must compare these three physical mediums directly against the four rules of network design. If we look at distance, fiber completely outpaces copper, carrying light signals across entire oceans where electrical impulses would simply die. For environment, coaxial handles the roughest physical conditions, while fiber offers perfect immunity to electrical noise. In bandwidth, fiber's light-based capacity easily dwarfs the broadband limits of both coaxial and standard Ethernet. But cost brings the final variable. Despite its absolute physical superiority, fiber is incredibly expensive to buy and labor-intensive to install. Twisted pair, by contrast, is exceptionally cheap. This matrix dictates the physical topology of our world. Cheap, reliable twisted pair connects individual office computers, while highly expensive fiber connects cities and continents. Look at the device you're using right now, or the router sitting in your home. Consider what specific physical cable is carrying this exact data to you at this very second. The invisible internet is actually a highly calculated triumph of physical engineering, perfectly balancing light, electricity, and economics to keep the globe connected. Consider the sheer volume of data moving across a network at any given second. Millions of devices constantly transmit billions of bits of raw information. Left to their own devices, these unformatted streams of data would inevitably collide. The resulting interference would cause the local network to collapse under its own weight. To survive this journey, data requires strict mechanical formatting and intelligent hardware to route it efficiently. This highly managed physical environment is known as the access layer, the exact point where devices connect to a wired local network. We are going to trace the exact path of a single message as it navigates this entire physical environment, starting from its initial formatting, moving through an algorithmic switch, and ending at its final delivery. Reliable local networking relies entirely on rigidly enforced data geometry and hardware logic executing flawlessly in milliseconds. Before any message can be transmitted, it must undergo encapsulation. This is the mandatory process of placing one message format securely inside another, creating a digital envelope designed for network delivery. In a local environment, this strict structural envelope is called an Ethernet frame. As we see in this diagram, the original message payload is completely enclosed by the rigid architecture of the frame. The frame is built with highly specific components. First, it requires the destination and source MAC addresses. These prepend the payload and provide the exact hardware routing points for both the sender and the receiver. Next, the frame incorporates a preamble and a start of frame delimiter, or SFD. These elements manage microsecond timing, synchronizing the sending and receiving devices before the data payload actually arrives. Finally, a frame check sequence is appended to the end. This acts as a strict quality control mechanism, scanning the entire wireframe structure to hunt down and identify any transmission errors. While the Ethernet frame governs local, physical movement, a separate system called the Internet Protocol, or IP, handles the broader external routing across interconnected global networks. Without this exact, sequentially perfect Ethernet frame format, network hardware will instantly drop and completely destroy the message. The physical environment where these frames travel is the access layer. This is the real-world threshold where individual devices gain their first-line entry into the wired network. Operating in this layer requires specific physical hardware: the host device's network card, an Ethernet cable, and a centralized multi-port networking switch. The Ethernet switch functions as the central traffic manager. It controls and directs all communication flowing through this physical layer. The access layer serves as the critical infrastructure that transforms isolated, standalone hosts into a cohesive, mechanically linked system. The primary challenge for the Ethernet switch is instantly sorting thousands of incoming frames and directing each one to its correct physical port. To solve this, the switch relies on an internal directory known as the MAC address table. Looking at this ledger, it tracks active ports in one column and their corresponding host MAC addresses in the other. When the switch accepts an inbound frame, it decodes the data to read the MAC address headers. It begins by extracting the source MAC address. The switch immediately learns from this data. It maps that extracted source MAC address directly to the physical port the frame just arrived on, dynamically logging it into the table. Next, the switch reads the frame's destination MAC address. It searches its newly updated ledger until it locks onto a matching MAC address, identifying exactly which port the target device is connected to. Upon finding a match, the switch constructs a temporary, dedicated circuit exclusively between the source and destination ports, completely bypassing all other available pathways. Ethernet switches do not rely on blind broadcasting. They use dynamic state mapping to turn chaotic network traffic into perfectly isolated point-to-point data pathways. Historically, the most destructive threat to network performance has been data collisions, instances where signals crash into each other while traveling along a shared wire. Modern Ethernet switches overcome this through a mechanical upgrade that allows the simultaneous sending and receiving of frames over the exact same cable. By building precise, temporary circuits derived from the MAC address table, the switch effectively isolates these bidirectional traffic streams, stopping crashes before they can occur. This dynamic circuit architecture ensures the network runs at peak efficiency, maintaining flawless data flow regardless of how many devices transmit simultaneously. Navigating this dedicated circuit, the perfectly routed Ethernet frame arrives safely at the destination host's physical port. Here, the recipient host initiates de-encapsulation, the process of reversing the sender's initial formatting sequence. The host mechanically removes the frame's structural metadata, stripping away the check sequence, the delimiter, and the MAC addresses, until only the pristine original payload remains for the computer to process. Every seamless digital interaction relies entirely on this hidden, continuous loop of strict encapsulation and highly organized algorithmic routing. Right now, literally billions of individual devices scattered across the globe are actively exchanging data across oceans in absolute milliseconds. So how does the exact data packet carrying the audio and visuals of this explainer navigate all that global chaos to find the specific screen you are looking at right now? It is a massive logistical problem. If the internet's core routers had to memorize the exact global location of every single smartphone and server, the hardware would instantly overload and collapse under the sheer volume of data. To solve this, digital transit borrows a basic rule from the physical postal service. Every single packet of data sent across the network requires both a clear source and a clear destination address. To get on the internet, your device is assigned an IPv4 address directly to its network interface card, creating the precise local identifier needed to process that transit. By assigning these specific addresses, the internet transforms a chaotic sea of hardware into an organized system of unique destinations, providing the basic order required to keep the global network from collapsing. If we look at the raw machine data, an IPv4 address is an unbroken string of 32 ones and zeros. Asking a human network engineer to manually configure hundreds of routers using massive blocks of binary code is a complete logistical nightmare. To make this readable, those 32 bits are sliced into 4 distinct 8-bit bytes, known as octets. The system then translates each of those binary octets into a decimal number, separating them with a period to create dotted decimal notation. This clean, human-readable format saves engineers sanity while simultaneously allowing the operating system to mathematically slice the address into distinct functional layers. This address architecture mirrors the structure of a traditional telephone system, splitting the 32 bits between a broad network area code and a specific host device number. But a computer looking at 4 decimal numbers does not naturally know where the broad network ends and the specific host begins. To define exactly where the network ends and the host begins, the system uses a mathematical filter called a subnet mask. A mask like 255.255.255.0 identifies the first 3 groups as the network, isolating the final group as the host. Any devices that share that exact same network portion exist on the same logical network. They exchange data back and forth locally without any outside interference. However, devices with different network portions are mathematically isolated. Even if you plug them into the exact same physical switch, they cannot talk until a router steps in to bridge the gap. This division elegantly separates physical proximity from logical organization. Engineers can build infinite, highly organized network structures entirely on shared hardware. This brings us back to that massive logistical threat: billions of individual devices overwhelming the internet's core hardware. The network and host hierarchy entirely bypasses this problem. When a packet travels the globe, the router only reads the broad network portion of the address, ignoring the individual device. The system only bothers to calculate the specific host location once the packet successfully lands inside the correct local network. By memorizing a map of broad networks instead of tracking billions of individual computers, global routers keep the data flowing without suffering catastrophic overloads. This hierarchical architecture provided the stable foundation that allowed the modern digital age to expand across the entire planet. Yet it contains a fatal mathematical flaw. Because the entire system relies on a strict 32-bit architecture, there are only about 4.3 billion unique address combinations physically available. Today, we have smartphones, smart TVs, and billions of new devices coming online every single year, each demanding their own address. The mathematical foundation that built the internet is exhausted. We have run out of numbers, forcing global engineers to scramble for a solution to humanity's next massive digital hurdle. Right now, across the globe, billions of devices are firing off unimaginable amounts of data. From streaming servers to smart appliances, the internet operates as a continuous, pulsing web of information exchange. The IPv4 protocol is built on a finite 32-bit architecture. This creates a hard numerical limit. The total number of unique IP addresses that can ever exist is exactly 4,294,967,296. There are currently over 15 billion connected devices operating globally. Based on that 32-bit limit alone, the network would have reached full capacity years ago. Beyond the address limit, if these billions of devices communicated without restrictions, the sheer volume of discovery traffic would overwhelm the hardware and stall the entire system. To function at this scale, the internet relies on two engineering solutions: network address translation and strict physical network segmentation. Managing this traffic requires an understanding of how devices communicate at Layer 3, which is categorized into three distinct transmission methods. The first is unicast. This is one-to-one communication, where a single source IP address routes a packet directly to a single destination IP. The second is multicast, an efficient one-to-many communication method. For a device to receive these packets, it must explicitly subscribe to a specific multicast group. Routing protocols use this to stay efficient. Routers running OSPF, for example, listen to the multicast address 224.0.0.5. When a packet arrives, only the participating routers process it, while other devices ignore the frame entirely to save CPU cycles. The third method is broadcast, a one-to-all transmission. This is triggered by an IP address where every bit in the host portion is set to 1. Unlike multicast, a broadcast forces every device on that network segment to stop its current task, accept the frame, and process the data. This makes broadcasts mandatory for finding other devices on a local network, but it also creates a recurring processing load for every connected machine. A device cannot function without these broadcasts. Upon booting, a computer must use the DHCP protocol to acquire an IP address, and ARP to resolve local MAC addresses. This diagram shows a flat LAN architecture with 400 users tied to a single router interface under the 172.16.0.0/16 address. The switches connecting these users are designed to propagate broadcast frames out of every interface except the one that received it, meaning they provide no boundary for this Layer 2 traffic. If hundreds of hosts are simultaneously sending ARP and DHCP requests, those broadcasts flood the entire switch fabric. This leads to a broadcast storm. The hardware becomes so occupied with processing these discovery frames that there is no CPU capacity or bandwidth left for actual data. Attempting to grow this network by simply adding more switches will eventually result in total performance collapse. To resolve this, network engineers use routers to create physical segments within the network. By design, a router does not forward broadcast frames. It acts as a barrier, containing that traffic to a single interface. Here, the original network is split into two isolated broadcast domains, separated by the router interfaces G0/0 and G0/1. This is achieved by subnetting, which involves borrowing bits from the host portion of the IP to change the prefix length. This transition from a /16 to TOM/24 networks creates two smaller, functional spaces. Now, an ARP broadcast originating in LAN 1 is stopped at interface G/0, ensuring that users in LAN 2 are not affected by the traffic. Subnetting also allows for a logical design that enhances security and organizational control. In this example of subnetting by location, each /24 network is mapped to a specific floor of a building, which simplifies troubleshooting. Alternatively, functional segmentation groups users by department, allowing an administrator to set security policies that prevent traffic from the student LAN from reaching human resources or accounting. Device-type segmentation can also keep noisy traffic from a printer LAN isolated from critical server infrastructure. This transformation replaces an unstable, flat topology with a secure, performant architecture. While subnetting manages internal traffic, it does not solve the global problem of having only 4.3 billion available addresses. This chart shows the original classful system from 1981, where Class A networks alone were allocated 50% of all available IPv4 addresses. Because a Class A block assigned over 16 million addresses to a single organization, early allocation was highly inefficient and accelerated address exhaustion throughout the 1990s. To address this, RFC 1918 established specific blocks of IP space to be reserved strictly for private use. These private ranges, such as 10. or 192.168, are not routable on the public internet. This allows millions of different internal networks to use the same addresses without conflict. This creates a new challenge. A device with a private, non-routable IP cannot communicate directly with a public website. Network Address Translation, or NAT, solves this at the edge router, which sits between the internal private LAN and the ISP's public cloud. When a device sends a packet to the internet, the router intercepts it and removes the private source IP address. The router replaces it with the organization's single public IP address before forwarding the packet to the ISP. The use of NAT delayed the depletion of the IPv4 address space for decades by allowing private expansion to continue independently of public address scarcity. Without intervention, a standard network would fail under the weight of its own discovery protocols. Subnetting uses routers as internal boundaries to contain broadcast traffic and enforce logical security. At the same time, those routers use NAT to act as translators, allowing massive private networks to operate behind a single public IP. Both processes occur simultaneously on every outbound packet, invisible to the users and devices relying on them. The reliability of the internet depends as much on these logical boundaries as it does on the physical infrastructure connecting them. The implementation of network segmentation and address translation provides the structural framework for a globally scalable internet. The legacy IPv4 routing protocol provided a theoretical maximum of 4.3 billion digital addresses. Today, that 32-bit pool is fully depleted. For years, network administrators relied on workarounds like network address translation, or NAT, to share remaining IP addresses. But the massive influx of mobile devices and the expanding Internet of Things has pushed NAT beyond its capacity, introducing significant network latency. These NAT routing limitations actively break modern peer-to-peer connectivity, rendering stopgap measures ineffective for modern infrastructure. The architectural solution to this exhaustion is the 128-bit IPv6 address space. By expanding the address length to 128 bits, IPv6 increases global routing capacity from 4.3 billion to 340 undecillion addresses, a number followed by 36 zeros. Successfully navigating this transition requires engineers to map the specific coexistence protocols keeping mixed networks online and deconstruct the strict hexadecimal syntax of the new system. Transitioning to IPv6 is a mandatory structural evolution required to keep the global internet operational. Global network architecture cannot transition to native IPv6 overnight. To maintain connectivity during this multi-year evolution, the IETF developed 3 primary migration bridges. The first technique is dual-stack coexistence. Dual-stack allows devices to run both IPv4 and IPv6 protocol stacks simultaneously on the same network segment, processing both traffic types natively without interference. The second technique, tunneling, is used when a modern IPv6 network is separated by legacy IPv4 infrastructure. To cross the legacy divide, a router encapsulates the IPv6 packet inside an IPv4 shell to traverse the older network. Once the payload arrives, the router strips the IPv4 shell to reveal the original IPv6 data. The third transition method is translation, specifically utilizing the NAT64 protocol. NAT64 functions as an active interpreter, translating an IPv6 packet into an IPv4 packet, and vice versa. This allows direct communication between completely distinct hardware systems. While dual-stack, tunneling, and translation maintain continuity across fragmented infrastructure, they remain transitional tools. The definitive objective is native end-to-end IPv6 communication. Upgrading the global infrastructure solves the physical capacity problem, but it introduces significant syntax challenges for the engineers managing this expanded routing space. To map 128 bits of data, IPv6 replaces the dotted decimal format of IPv4 with a base 16 mathematical structure. 16 binary digits translate into a 4-digit hexadecimal block. This allows administrators to use digits 0 through 9 and letters A through F to represent address values. This 16-bit segment is officially known as a hextet, the foundational building block of the system. A complete IPv6 coordinate consists of exactly 8 of these hextets strung together. Unlike the periods used in IPv4, these hextets are separated by colons. Writing out all 8 hextets using the full 32 hexadecimal characters creates the preferred format. While the preferred format provides absolute mapping precision, a massive 32-character string is incredibly difficult for human network administrators to configure manually without making critical errors. To shrink this bloated format into a manageable state, administrators apply strict mathematical compression rules. The first compression protocol is the omission of leading zeros. Within an individual hextet, any starting zero can be dropped. As seen in the first row, 0db8 compresses to db8. Similarly, if a hextet consists entirely of 4 zeros, the first 3 leading zeros are dropped, leaving a single zero. This rule strictly applies to leading zeros. You can never drop a trailing zero. Dropping a zero from the end of a hextet alters the base 16 mathematical value. This introduces total ambiguity and renders the network map unreadable. Applying Rule 1 significantly reduces visual clutter, but the address still contains multiple isolated zeros that require further compression. For maximum efficiency, engineers utilize Rule 2, the double colon. A double colon completely replaces any single, contiguous string of hextets consisting entirely of zeros. This collapses massive blocks of routing data into 2 punctuation marks. However, the architecture enforces an absolute constraint. The double colon can only be used once per address. Applying it twice prevents routing hardware from calculating how many 0 hextets belong to each colon. This results in multiple incorrect address possibilities and immediate system failure. Consequently, the primary best practice is to apply the double colon to the longest contiguous string of zeros in the address. If an address contains 2 strings of zeros of the exact same length, the double colon is applied to the first string. Combining Rule 1 and Rule 2 successfully crushes a 128-bit string into the elegant and efficient compressed format. The migration away from IPv4 is a massive structural evolution of global digital infrastructure, expanding to accommodate billions of new endpoints. Coexistence mechanisms, dual stack, tunneling, and translation serve as the bridges keeping legacy hardware communicating with modern networks. Yet the efficiency of this system relies on the administrator. Only through the strict application of base 16 compression rules does the infinite scale of a 128-bit protocol become human manageable. Mastering these transitional bridges and the mathematics of the syntax is the requirement for navigating the routing architecture of tomorrow.